Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you to this session. This week we are going to revise heat and thermodynamics and we will be covering several subtopics this week. For example, thermal expansion, calorimetry, kinetic theory of gases, heat transfer, and first law of thermodynamics as well. Okay, so today we will be starting with thermal expansion. Okay, so without losing any further time, let's share our screen. So here we go. So as we know that if the temperature of the body increases in general, its size will also increase, because when a body is heated up, vibrational energy of molecule increases, so amplitude of the vibration will also increase, so average separation between the molecule increases as well, so they will be needing more space between them. Okay, so that can happen only by increasing the size. Okay, and see, like solid, liquid, gas, all sort of things, their volume increases with a raise in temperature. But here in this chapter we will be restricting our discussion to the thermal expansion of solids and liquids only. And here the most of the focus will be on solid mainly. Okay, so let's first talk about linear expansion. Okay, let's first talk about linear expansion over. Okay, so let's say we have a thin rod of uniform cross section, okay, whose length is L at let's say a temperature theta degree Celsius. Okay, and when the temperature is increased by d theta, you can say. Okay, so then one thing we are interested in, and that is relative change in length, and that quantity got to be dl by L, and this dl by L, that is relative change in length, is directly proportional to change in temperature. Dl by L is directly proportional to change in temperature. So let's introduce a proportionality constant as well. So dl by L would be equal to alpha into d theta, where alpha is the proportionality constant, and let me name it, where alpha is nothing but coefficient of linear expansion, you must say, coefficient of linear expansion. Okay, and that is nothing but one of the property of this material over here. Okay, and see, this coefficient of linear expansion, that will be a function of temperature. Okay, but for small change in temperature we can assume the alpha to be constant. Okay, so this is the equation we are having for the relative change in length, okay, of a rod. Okay, so here we are interested in finding out the final length at, let's say, for example, theta plus at some final temperature, you can say. So let's try to have that. Okay, so the differential equation we are having is dl by L is equal to alpha d theta, and let's integrate both sides with proper limits. So let's say at theta is equal to, let's say, some theta I. Okay, the initial length is L naught, and at theta is equal to theta F, we want to find out this length. And solving this, it will give us ln L upon L naught, and that would be equal to simply alpha delta theta, you can say. And you should realize when you will be rearranging, so that it will be giving you L is equal to L naught into e to the power alpha delta theta. So this is the, you can say, final length of the rod over here, and this L naught is initial length, alpha is nothing but the coefficient of linear expansion, and delta theta is change in temperature. So this is the expression. So for most of the solids or liquids, one approximation we are going to use, one assumption we are going to have over here, and which is going to be very, very useful in this chapter. So let me say, like, for most solids and liquids, the coefficient of linear expansion, like alpha, is a very small quantity. Alpha is much less than 1, like order of you can say 10 to the power minus 5, 10 to the power minus 6, etc. Okay, so if this quantity is very small, delta theta will also be not much greater than 100 degrees Celsius, etc. So in that case, you can see that alpha delta theta would be very small. Okay, that is much less than 1 over here. So what we can say, as we all know, the expansion of e to the power x is nothing but 1 plus x upon factorial 1 plus x square by factorial 2 and x cube by factorial 3, and this is an infinite series. Okay, so if we ignore the higher power, like for example, if x is much less than 1, we can ignore the higher power. All these terms could be ignored. So e to the power x will be approximately equal to 1 plus x. So in that case, this expression over here can be approximated as L is equal to L naught into 1 plus alpha delta theta over here. And always understand, this equation we can use only when alpha delta theta, let me write it over again. So alpha delta theta is very small in comparison to 1 over here. So this is the expression we will be using for the linear expansion. Okay, so now the thing is, like there are a lot of physical quantity which we measure by measuring the length. Okay, like for example, if we directly want to measure the distance between 2 points, we can use some scale, and if that scale is made up of some kind of metal, and metal have relatively greater value of alpha, so like there would be a significant linear expansion in that. Okay, and due to this linear expansion, due to increase in temperature, errors are bound to happen. Okay, so let's look at few cases. Okay, one case I will take, that is error in measurement of distance using metallic scale. And let's try to understand this by taking one example. Okay, and you should understand, like for example, there is a scale over here, and there would be several markings on that scale. Okay, so this smallest division which this scale can measure is known as the least count. Okay, so least count. Okay, so let's say this is the situation, say at theta uh, degrees Celsius. So if the temperature is increased by delta theta, so that theta plus delta theta degrees Celsius, what will happen? Okay, so you should realize, like there would be like both the all these markings will be a little bit expanded. Okay, like for example, this is, you can say, if this is LC naught and this is LC, so LC will simply be equal to, LC will be equal to LC naught into 1 plus alpha delta theta, for example. So let's say it is calibrated to measure correctly at theta degrees Celsius, and let's say this is original least count. Okay, so at theta plus delta theta degrees Celsius, you must realize, since least count is increasing, although it would be reading 1 centimeter only, but the actual value here is 1 plus alpha delta theta centimeter, that you should realize. So the actual length, you can say the actual length over here, that would be nothing but the reading, and that multiplied with the least count. Okay, and least count is liable for a change due to thermal expansion over here. Let's say, let's take one example, simple example over here. Let's say, suppose a steel tape is calibrated at 35 degrees Celsius. Let's take an example that steel tape is calibrated at 35 degrees Celsius, means it will measure correctly at 35 degrees Celsius. And let's say at 50 degrees Celsius, it measures the distance between 2 points, between 2 points as, say, something like 10 centimeter it is measuring. Okay, so what would be the actual distance between those 2 points? So actual distance, the formula we can use is simple. This reading is equal to length is equal to reading into least count. So reading definitely is 10 centimeter. So this 1 centimeter is not exactly 1 centimeter at 50 degrees Celsius. Only you can say like 10 least count. This is the change least count. So reading is 10. Okay, and the least count at 50 degrees Celsius would be nothing but that would be simply 1 centimeter is the original least count. We are using this formula into 1 plus alpha delta theta, and alpha would be nothing but the coefficient of linear expansion of this metallic scale, and delta theta is the change in temperature. Like in this case, the delta theta is 50 minus 35, which is 15 degrees Celsius. So this is how the error occurs when we use some metallic scale, okay, in order to measure the distance between 2 points. Let's have one another situation where an error can occur. Another situation I'm going to take is, that is, error in measurement of time, okay, using simple pendulum. Okay, simple pendulum, you understand, okay, is a string, let's say metallic string we are having, and some bob is suspended, and we just measure the time of oscillation. And you understand, if this length is L, okay, of the string, the time period would be nothing but 2 pi root under L by G. Okay, so let's say if the temperature is increased due to change in temperature, okay, this L will change also, and when this L will change, this T will change also. So relative change in time period delta T by T, we can safely write that would be half into delta L by L over here. Okay, and delta L by L, this quantity we have already got, that would be nothing but half into alpha delta theta. Okay, so this is the relative error in the measurement of time period. So you should realize that if temperature increases, okay, the time period of simple pendulum will also increase. That means pendulum will now take more time to complete one oscillation. So clock will become slow. At higher temperature, the clock is gonna become slow, and at lower temperature, okay, the clock will become fast. Okay, so this thing you must understand. Like for example, if this kind of question is asked to you, like for example, by how much time, okay, a pendulum clock will become slow in an increased temperature in a day, you can say. So you should realize in that case, since capital T, the time period, is nothing but the total time of oscillation divided by number of oscillation. So it should be clear that delta T by T would be same as delta small t by T, where delta small t by T is nothing but the relative change in measurement of time. Okay, capital T is time period, small t is the total time over here. So you can also write like delta T by T, that would be equal to capital T by T over here, and that will be equal to half alpha delta theta. So if somebody is asking like by how much it will become slow, so simply delta T you can find out, that is half alpha delta theta into, for the time which you are finding out the uh, uh, error. Okay, like for example, 1 day, if it is, so 1 day is basically in second, if you want to find out in SI unit, so 1 day would be nothing but 24 hours into 3600 second, etc. And the value of alpha and value of delta theta you must be knowing. So that is how you can solve this kind of question. Okay, so another thing I want to tell you here about this chapter, like this chapter, okay, the approximation is very, very important. You must be able to use the proper approximation at proper time. Okay, so let me have one example over here. So let's say we have three rods. Okay, and they form a equilateral triangle, okay, at some temperature, and they are hinged at their ends. Okay, so let's say this is A, B, and C, and AB and AC are made up of same material. Let's say coefficient of their linear expansion is alpha 1 and alpha 1, but the BC is made up of some different material. So let's say that is alpha 2, and all the rods are identical in area of cross section and length, only their coefficient of linear expansion are different. Okay, so at some temperature you can say they are forming an equilateral triangle, means the angle between the two rods here will be equal to 60 degree. So if the temperature is raised by, let's say, delta theta over here, okay, uh, we want to find out the calculate in change of this angle, how much by this angle theta will change. You can see that its initial value, theta initial, is nothing but 60 degree, you can say. So we want to find out like what would be the change in theta or delta theta. We want to find out if the temperature is, you can say, if temperature is raised by, say, delta T. Okay, temperature is raised by delta T. So for that, what we are gonna do, let's try to approach this problem. So let's look at this right angle triangle. Let's say this point is D. So you should realize, okay, so at any instant, even if there is thermal expansion, okay, if this angle is theta, so this gonna be theta by 2 over here. So you should realize now, like if I am gonna write sine theta by 2, sine theta by 2 is going to be nothing but BD by AD, BD by AD, and the length BD will change and length AD will change when temperature is changed. Okay, and let's say this like T is equal to 0 degrees Celsius, we are taking the reference temperature. So this BD will be simply nothing but you can say BD naught, or initial value you can say BD naught, um, into, and that would be 1 plus alpha 2 times T, and that would be AB naught, sorry, rather it should be A, B you should write, so that would be AB naught into 1 plus alpha 1 T over here. So when you will be rearranging this quantity, the initial value of that thing you should realize is nothing but half. So half into, and now this term, like see, this term here is small and this term here is small. So using the binomial approximation, you should realize this denominator will go above, and that would be 1 minus alpha T. And when that will be multiplied with this quantity, effectively you will be getting 1 plus alpha 2 minus alpha 1 into T. So this is the expression we are having, that is sine theta by 2. Okay, so at any temperature T, okay, this is the angle between, okay, this AB and AC side. So now we are looking for d theta. So what we can do, we can differentiate both sides. So differentiating both sides will give you cos theta by 2 into, you can say, d theta by 2, and that would be nothing but half into alpha 2 minus alpha 1 into dt. Okay, so clearly, for example, this 2 will get cancelled over here. So d theta, you can say, is nothing but alpha 2 minus alpha 1 upon cos theta by 2 over here. Okay, and this is dt. Okay, and integrating those, like for example, simple delta theta will be nothing but alpha 2 minus alpha 1, and you can take the initial value of theta at theta is equal to 60 degree we are asking. So cos 30 degree would be nothing but here root 3 by 2 into delta t, and you can substitute these values if they are given, and delta t etc., in order to get the answer. So that was one of the question. One another interesting question I want to take here is the case of bimetallic strip. That is one of the interesting case in this topic. See, let's say we have a bimetallic strip. Bimetallic strip means, okay, this strip is made up of two materials which has been aligned parallel like this. Okay, the only thing is their coefficient of linear expansion alpha 1 and alpha 2, let's say, are different. Okay, and let's say their cross sectional areas etc are same. So let's say their thickness is t. The bimetallic strip has their thickness at as t. So let's say at theta degree Celsius, let's say its length is L at theta. Okay, and we like if the temperature is changed at theta, this is basically straight that you can see in the diagram. But when the temperature will be changed, okay, since coefficient of linear expansion are different for both the materials, they will try to expand by different lengths over here. So that is why for example, if alpha 1 is greater than alpha 2, the upper rod will try to expand more and the lower rod will try to expand less. So due to that, this bimetallic strip will bend, okay, and it will take the shape of an arc, you can say. It will take the shape of an arc. So when it is taking the shape of an arc, you must realize, and then we become interested in finding out the radius of curvature or mean radius of curvature of this. Let's say, so this curve, let's say this arc has been formed, and let's say this C is the center of curvature of it. And let's say the mean radius of curvature would be this quantity here. So this is say R, and we are interested in finding out R if the temperature is increased by delta theta. So what we are gonna do here? So one thing you realize, so see, this would be the, you can say, mean length after the expansion. Okay, so you should realize first of all the distance of this line from the center is going to be nothing but that is going to be R minus t by 2, because this length is t, so half of it would be t by 2, and from here to here total it is r, so that is r minus t by 2. And if we take the mean position of the outer rod, so this is going to be r plus t by 2 over here, and let's say it subtends an angle, okay, phi at the center. So what we can write over here, um, let's name it also, or let's say this point is A and this point is B and this point is C and this point is D. So AB, the length of arc AB is gonna be equal to R plus AB, that would be R minus T by 2 times theta over here. And that should be equal to, after the thermal expansion, the length AB would be nothing but L into 1 plus, we are looking at the lower one, so 1 plus alpha 2 delta theta. Okay, so this is AB, and similarly CD you can write it as, that would be R plus T by 2 times theta into L multiplied with 1 plus alpha 1 delta theta. So basically this is equation 1 and this is equation 2, and if you divide equation 2 by equation 1, what you will be getting over here is, so let's say this is 1 alpha 1, you will be getting here is 1 plus alpha 1 delta theta divided by 1 plus alpha 2 delta theta, and that will be equal to R plus T by 2 divided by R minus T by 2 over here. And when you will be applying componendo and dividendo, let's say, for example, A by B is equal to C by D. So that would be A plus B upon A minus B is equal to C plus D upon C minus D, etc. When you will be applying that thing. So in numerator, you will be writing the sum of these two quantities. So that would be 2 plus alpha 1 plus alpha 2 times delta theta, and in denominator we will be having alpha 1 minus alpha 2 times delta theta, and right hand side you will be getting the numerator would be simply 2r and denominator would be t over here. Okay, so this expression, like for example for r, now we can write down that is t by 2, and in the bracket you will be having 2 plus alpha 1 plus alpha 2 times delta theta, and that divided by alpha 1 minus alpha 2 times delta theta over here. And now you should realize when you look at the numerator, that is 2 plus this quantity, and this quantity is very, very small in comparison to 2, so we are ready to ignore that. So what we will be left of with this 2, and this 2 will also get cancelled, so this thing will be approximately equal to T upon alpha 1 minus alpha 2 times delta theta. So the main thing to notice in this expression over here, that this radius of curvature here would be directly proportional to, or inversely proportional to, you can say, alpha 1 minus alpha 2. Obviously it is also inversely proportional to delta theta, you should realize. But see, for example, if alpha 1 and alpha 2 would have been same, so like this expression will be tending to infinity, so there will be no bending of this bimetallic strip over here. So that thing you should realize. Okay, this was the famous problem of bimetallic strip. And now let's look into some other concepts over here, and now I will be dealing with the concept of thermal stress. Thermal stress. So imagine we have a rod, okay, and which is fixed between two rigid ends, rigid walls, let's say, and let's say the length of this rod is L, and coefficient of linear expansion is alpha, and Young's modulus is y over here, and let's say this is at theta degree Celsius. At theta degree Celsius, there is no like this is a rod without any stress in it. There is no stress right now. Okay, so what I'm gonna do over here, like if or when temperature is increased by delta theta here, so what will happen? Okay, so this rod will try to expand. Okay, so if this rod would have been free, if this rod would have been free, what would have been its expansion? Let's say delta L. Delta L would have been L alpha delta theta. And the thermal expansion formula we know, let's say this is nothing but the thermal expansion if rod was free to expand. Rod was free to expand. Okay, so and also you should realize, for example, now see, so due to these rigid supports, okay, this rod was not allowed to expand by this much value. This is not getting allowed to expand because it is in a strained condition, so it will be having like at raised temperature, it is in strained condition because its natural length would have been L plus L alpha delta theta, but its length right now is L only. So it is clear that it is in strained position. So there would be a thermal stress sigma from both the side. Like what would be the value of sigma, we want to find out over here. So let's try to find out. Due to this sigma over here, there would be some this is compressive stress, so there would be some compression. Let's write it as delta L, and delta L, according to our formula, we will simply write that would be stress into length upon Young's modulus over here, and that thing you can say that is compression due to compressive stress. Okay, so now the thing to notice over here is a net change in the length of the rod is equal to 0. So net change of the in the length of the rod, that would be delta small l plus delta capital L. So delta small l plus delta capital L got to be equal to 0, because here this rigid support is not allowing this rod to expand. So this quantity is going to be 0. So when you will be rearranging, so L alpha delta theta, you will be getting as sigma L by Y. And just by rearranging sigma, you will be getting as Y alpha delta theta. So this is an important expression. This is the expression for thermal stress. Okay, so this rod is under this much thermal stress, and that thermal stress is compressive in nature. So let's look at a few examples in which we will be having thermal stress, and let's look at some famous problems. Okay, one famous problem is of the composite rod. Now you see, let's say between two rigid supports, we have fixed a composite rod. Composite rod means like two rods of different materials but having same cross sectional area are joined together like this. Okay, and let's say the parameters are its length is L1 and coefficient of linear expansion is alpha 1 and Young modulus is y1, and similarly for this L2 alpha 2 and y2 over here, and this is the junction between them. Okay, this is the junction. So initially, at let's say theta degrees Celsius, this rod is not having any stress present inside it. So now my question is, like, when temperature is raised by delta theta, okay, let's find out, like, first thing, what would be the thermal stress in the rod, okay, the whole rod. And see, this is the junction over here. This point is junction. Okay, so due to this thermal expansion, the both the rod will try to expand differently. So there would be some displacement of this junction also, and we wish to find out that quantity, that is displacement of junction. These two things we want to find out over here. So what we are going to do. Okay, so when the temperature is raised by delta theta, so both of the rod will try to expand here. Okay, and due to thermal strain, but see this there is some support from both the sides, so that will not allow both the rods to expand freely. Okay, so both the rods will be under some thermal stress, and see, since the area of cross section is uniform, that thermal stress would be uniform as well. So let's say from this end on this rod, this is the thermal stress sigma and sigma. So on the another rod, the thermal stress would be same sigma and sigma. And you should realize both the rods are here experiencing the compressive stress over here. Okay, so how can we proceed with this? So let's look at the answer for the first part. So let's write net change in length of, say, rod 1. Okay, and rod 1 would be expanding due to thermal expansion, and it would be compressed due to thermal stress. So like in the previous question, we learned to write like small delta small l plus delta capital L. For the rod 1, like this quantity delta small l is gonna be equal to, like we learned in the previous question, that is going to be L1 alpha 1 delta theta. Okay, that is expansion due to the thermal expansion. Okay, and due to the thermal stress, it will get compressed by little, so that would be, you can say, sigma L1 by Y1. Notice this negative sign over here because it would be under the compressive stress over here. And similarly, net change in the length of the rod 2, you can write it as delta L2 plus delta capital L2 over here, and that would be equal to simply L2 alpha 2 delta theta minus sigma L2 by Y2. And notice sigma is same in both the cases because both the rods are experiencing same thermal stress because they are having same cross sectional area. And between this end and this end, okay, the net change in the length of the composite rod is equal to 0. So the sum of this quantity and this quantity is going to be equal to 0. So when we will be adding this and this quantity and equating it to equal to 0, what we will be getting here is L1 alpha 1, L2 alpha 2, and delta theta we can take common, and the another term we would be having, and that will be gone to another side, so that would be sigma into L1 by Y1 plus L2 by Y2 over here. Okay, so this relationship clearly gives us the value of sigma, and that will be equal to nothing but L1 alpha 1 plus L2 alpha 2 divided by L1 by Y1 plus L2 by Y2 over here, and that multiplied with delta theta over here. So that is the answer for the first question, you should realize. And now let's look at the answer for the second part. Okay, and that is the displacement of the junction. Now, displacement of the junction, you can say, since this end is fixed, so whatever is the elongation of any, like this rod will be elongated this side, and this rod, like kind of, you can say, one is getting elongated and another is compressed. So let's say the first rod is getting elongated, so this gap here is going to be the displacement of junction, and this gap is nothing but either of these quantities, either this you can say or either this you can say. So let's try to calculate the above quantity. So the displacement of junction, you must realize, that is going to be L1 alpha 1 delta theta minus sigma L1 by Y1, and value of sigma we have already calculated. So when we will be substituting that value over here, what we will be getting is L1 alpha 1 delta theta and L1 by Y1, let's keep it aside, and the value of sigma which we have found out is L1 alpha 1 plus L2 alpha 2 divided by L1 by Y1 plus L2 by Y2 here into delta theta. And now you should realize, rearranging this, it will be giving us L1 L2 delta theta and alpha 1 Y1 plus alpha 2 Y2, and that divided by L1 Y2 plus L2 Y1 over here. So that was one of the famous question. Let's look at another famous question very quickly, and this famous question is the trimetallic strip. Say we have a trimetallic strip, means a strip made up of three materials. Okay, so one material is sandwiched over between the two other materials. So let's say the outer material are same. Let's say the coefficient of linear expansion is alpha 1 and alpha 1 for the outer ones, and the coefficient of linear expansion for the middle one is different. Let's say that is alpha 2, and Young's moduli are, let's say, y1 and y1 for the outer material, and for the inner material it is y2 over here. So rod of equal lengths we are having and equal cross section of each strip we are having, and we wish to find out the length of system at, let's say, when the temperature is increased by delta theta. Okay, so again you should realize if alpha 1 and alpha 2 are different, let's say alpha 1 is greater than alpha 2, so the outer materials will try to expand more and the inner material will try to expand less, and in this quest they will be exerting some stress over each other. So if the outer one is trying to expand more, okay, so what we or let's say the inner one, or other way around also you can write. So let's have the inner one expand more, for instance. Okay, so in that case, basically the length they will be expanding will be same in that case. And let's try to do it this way. So let's say it is try to expand less, so the inner material will try to exert some thermal stress over it. So let's say sigma and sigma, and similarly it will also experience elongative stress or tensile stress, you can say, sigma and sigma. And this, the inner material will experience 2 sigma due to each up and low categories. Okay, so 2 sigma is the stress experienced by the inner material over here. And now you should realize that the outer materials are under elongative stress or tensile stress, but the inner material, that sandwiched material, is under the compressive stress. And the idea we are going to apply is same. So they will be basically expanding to the same length, so the change in length of the each rod will be same. So what we can say here, that delta small l1 plus delta capital L1, that would be equal to delta small l2 plus delta capital L2. So let's write delta L1 over here, so that you can see that would be due to thermal expansion, that would be L naught into alpha 1 into delta theta over here. And now you see the upper rod, this rod 1 over here, is under the elongative stress, tensile stress. So due to the tensile stress, it would be expanding here only, and that quantity is going to be sigma L naught by Y naught over here. And delta, this quantity, when we will be writing for due to thermal expansion, it would be L naught into alpha 2 and delta theta. And now you should realize the middle one is under compressive stress, so it will compress under that stress, and the stress is 2 sigma, to 2 sigma into L naught upon y2, you can write over here. So rearranging this, we are getting sigma into 1 by y1 plus 2 by y2 over here is equal to alpha 2 minus alpha 1 delta theta. Okay, so clearly this gives us the value of sigma, and that would be alpha 2 minus alpha 1 into delta theta divided by 1 by y1 plus 2 by y2 over here. So this is the stress. Okay, the value of sigma. So obviously the middle one is experiencing double the stress. The final length, when we are looking at the final length, when we are looking at, so you can write either of these terms, either this or that. So let's choose to write it as delta L1 plus delta capital L1, and we have already got its value. Let's substitute the value. Okay, so this quantity it would be, so L naught you can take common. Okay, and alpha 1 delta theta, and we will be writing sigma by y. This is basically y1 here. So sigma by y1. So 1 by y1 let's take out, and let's put the value of sigma over here. So alpha 2 minus alpha 1 uh, divided by here, that would be 1 by y1 plus 2 by y2 into delta theta also. And this is the elongation. So initial length, let's say its initial length was equal to L naught, so plus L naught you must also add. Okay, so the solving this will be giving the L naught and delta theta we can take common from the first term, and the finally you will be getting over here is 2 alpha 1 y1 plus alpha 2 y2 upon y2 plus 2y1 over here, and obviously plus L naught at the last. So this would be the final length. Okay, so this was one of the important question. Let's look at one another model of the question, and this is the question here. So let's say you have a smooth horizontal surface, and that smooth horizontal surface we have placed a composite rod. Okay, let's say that is made up of three materials. Okay, and their parameters, let's say the mass of these materials are m, 2m and 3m, etc., and its length is L, 2L and 3L, etc. Okay, and the coefficient of linear expansion is, let's say, alpha, 2 alpha and 3 alpha, etc. This is a trimetallic strip, you can say, and they are joined in series with each other. Let's say this end is A, B, C, D over here. So right now, at some theta degrees Celsius, um, this is without any stress. Okay, so now what we are trying to do over here, if we increase the temperature by T, let's say if we increase the temperature by T, all these rods are gonna expand. Okay, and this, they are kept on a smooth horizontal surface, so they will be expanding freely, so there will be no stress in it. Okay, so and let me also tell you, like L alpha T, that would be the value of delta L by L in this rod. Like this value is given to you as E, and you have to give your answer in terms of E, and E is a very small quantity, obviously, like the assumption we used to take. Okay, so we have to find out, like in this case, what would be the displacement of this end A, and what would be the displacement of this end D. These two things we have to find out. So how are we going to approach this problem? So the key idea to solve this question is, although these rods will be expanding, okay, due to thermal expansion, but only the internal forces will be responsible for the expansion, and due to the internal force, okay, the acceleration of center of mass will be equal to 0, velocity of center of mass will be equal to 0. So the displacement of center of mass of this three rod system is going to be equal to 0, although there would be the displacement of point A, B, C and D, etc., but the displacement of center of mass is going to be 0 only. Okay, so let's try to use this idea in order to solve this question, and let's take some parameters over here. So let's say this end is expanding by so this end is displacing by XA, this by XB, and let's say this is by XC, and this is by XD over here. Okay, and one thing you should realize, first of all, that the elongation in this rod is going to be L alpha T. So that is equal to E. Elongation in this rod is going to be 2L into 2 alpha into T. So that got to be 4E. And the elongation in this rod is going to be 3 alpha, 3L, 3 alpha into T. So 9L alpha T. So that elongation in this rod is going to be 9E over here. Okay, so now you should realize, first of all, is see, so XA, this is the displacement of point A and this is the displacement of point B, and center of mass of this uniform rod would be somewhere over here. So the displacement of center of mass of AB, the displacement of center of mass of AB, you can say that would be nothing but XA plus XB by 2, and similarly for XBC, COM you can write, that would be equal to nothing but XB plus XC by 2. The midpoint would be displacing by that much. And similarly for XCD, the center of mass of the CD part will be getting displaced by XC plus XD by 2. That you should realize. Okay. And another thing you should realize is, let's say this end is moving by XA. So XB we can write, XB would be nothing but XA. due to the movement of this, and apart from that this is getting elongated by E. So xb is xa plus E we can write, and similarly xc we can write it as xb plus this distance 4e, and xb is nothing but xa plus E, so that is going to be nothing but xa plus 5e. And similarly xd, in terms of xa and E you can write that would be xa, and the total elongation is 9 plus 4 plus 1, so that would be nothing but xa plus 14e over here. So now we are ready to use this thing, and the concept which we are going to use, that the displacement of center of mass of this whole thing is going to be equal to 0. So displacement of center of mass we can write it as m1 x1 plus m2 x2 etc. So like the mass of the first AB part is m, and displacement of center of mass of the first part is xa plus xb by 2 plus 2m is the for the second rod, and that would be xb plus xc by 2, and for the third rod that would be 3m into xc plus xd by 2, and that got to be equal to 0. So now let's further simplify it. Okay, so further simplifying it, m will get cancelled both sides. Okay, and you will be having xa plus 3xb plus 5xc plus 3xd over here, and that will be equal to 0, and that will give us, like for example xb, xc and xd we were able to write in terms of xa and E. Okay, so that would be xa plus 3 times xb was nothing but xa plus E, and 5 times this was nothing but xa plus 5e, and 3 times, and this was nothing but xa plus 14e it was there. Okay, and uh, you will be having finally that would be 12xa plus 70e, and that will give you equal to 0, and that will simply give you xa is equal to, that would be simply minus 35e by 6. Okay, so basically point A will be shifting effectively leftward, and xd also you can write xd is this quantity, xd is equal to xa plus 14e, so that will be giving you 49e by 6. So that was one very interesting question. So we have talked enough about linear expansion, and let's now talk about uh, areal expansion and volume expansion. And we will be restricting our discussion for isotropic material, that is for which physical properties are independent of orientation. So the coefficient of linear expansion in any direction is going to be same. Okay, so first of all let's have for areal expansion, and that is also known as superficial, or you can say areal expansion. Okay, so clearly, okay, delta A by A, you can write it as 2 times delta L by L over here. Okay, and delta L by L we clearly know is nothing but alpha delta theta, so that would be 2 alpha delta theta, and 2 alpha we know it as beta, so beta delta theta, and beta is known as coefficient of superficial expansion or coefficient of areal expansion. Obviously you can realize that beta is equal to 2 alpha. In that case, the final length a dash, let's say, you can write it as a into 1 plus beta delta theta etc., where beta is coefficient of superficial expansion. So that is it. And for the volume expansion, let's try to have a look at that thing, volume expansion. So for volume expansion, clearly delta V by V will be nothing but 3 times delta L by L, and that would be 3 alpha delta theta, and that we 3 alpha we write it as a gamma delta theta. Okay, so gamma you should realize is nothing but equal to 3 alpha, and that is coefficient of volume expansion. So in that case, V dash you can write it as V into 1 plus gamma delta theta. So relationship between alpha, beta, and gamma, you can say alpha is equal to beta by 2 is equal to gamma by 3, etc. Okay, so these terms are interrelated for an isotropic material. Okay, please understand that. Okay, so this was for the volume expansion and superficial expansion. Let's try to have one question quickly about the apparent expansion of liquid in container. Okay, so let's say inside a container liquid is completely filled, and the container has volume V naught. So if it is completely filled, the volume of the liquid is V naught as well. And let's say coefficient of linear expansion of the container is alpha C, and the coefficient of volume expansion of the liquid is nothing but gamma L. And when the temperature is increased by delta theta, the volume of liquid will become nothing but V naught into 1 plus gamma L delta theta, and the volume of the container will become Vc will be equal to V naught into 1 plus, and the volume expansion coefficient would be nothing but 3 alpha C over here, as we have seen already. So this would be the term over here. So now you see the apparent expansion of the liquid, you can say apparent expansion of liquid here will be nothing but whatever the volume of the liquid will overflow from this container, you can say, and that would be nothing but VL minus VC, and that will turn out to be gamma L minus 3 alpha C into delta theta, and I will write it as gamma apparent into delta theta, where you should realize that gamma apparent, which is apparent coefficient of volume expansion of the liquid, is nothing but gamma L minus 3 alpha C. So that was one of the interesting thing. Okay, and now due to change in volume, okay, of the solid, and mass remaining same, there will be change in density of the solid due to thermal expansion, and let's look at that aspect. So change in density due to thermal expansion. So let's say we have a material whose mass is m and volume is v at some temperature theta. So rho is related with mass and volume like this. So rho is equal to mass upon volume. And if the temperature is raised by delta theta, then rho dash will become something like m upon v dash. M will not change, but volume will increase. So you can write it as v dash, as we already know, is nothing but v into 1 plus gamma delta theta, and m by v is nothing but a rho. So you can write it as rho dash is equal to rho upon 1 plus gamma delta theta over here. So that you should realize. And also you can use the binomial approximation. Rho dash will be equal to rho into 1 minus delta theta over here. So that is another approximation, you can say. So one very quick question, let's see, which is related to the change in density. And this question is, let's say we have a solid cylinder. Let's say a solid cylinder we have, okay, of uniform cross section, and is floating in a liquid, and the coefficient of linear expansion that has been given of the solid uh, is alpha S. Okay, and let's say coefficient of volume expansion of the liquid in which it is floating is given to you as gamma L. Now the temperature of the system is increased. The whole system is solid as well as liquid has been increased, and we have to find out the value of gamma such that, okay, the first part of the question is such that the fraction of volume of submerged cylinder okay, doesn't change. That is the first part. And the second part is, let's say, depth of the submerged cylinder. Depth of submerged cylinder does not changes. So these two questions we want to look at. Okay, so imagine, so this is the cylinder which is floating in a liquid. Let's say floating in a liquid, and density of liquid is rho L. Okay, and density of this solid is rho S. Okay, and let's say its total volume is V, and the submerged volume is Vs only. Okay, so as we know, the fraction of submerged volume Vs by V is given by nothing but rho S by rho L over here. We have already looked at this expression when we were dealing with the Archimedes principle. Okay, so now you should realize this we do not want to change. Like this fraction of volume submerged cylinder does not, we don't want it to change. Okay, so like let's say this is at changed temperature, so this could be written as simply rho S can be written as rho S naught upon 1 plus, you can write it as 3 alpha S into delta theta. So that is the density, change density. We have already looked at this formula over here, the above formula. Okay, and rho L, we can write it as rho L naught into, that would be 1 plus gamma L delta theta over here. So now it's time for us to um, use the approximation rho S naught by rho L naught. Let's take it apart, and this quantity, combining this and this quantity, will give us 1 plus gamma L minus 3 alpha S into delta theta. Okay, and see, this value we do not want to change, so this term should be equal to 0 in that case. So in order for this term to be equal to 0, this term got to be equal to 0. So gamma L is equal to 3 alpha S is the answer for the first part. Now for the second part, let's look closely, although it look like both the question are in fact same. So since we are writing like Vs by V is rho S by rho L over here, okay, and that can also be written as like cross sectional area, whatever is the cross sectional area for the submerged part and the total part, that is going to be same. So height of submerged part upon the total height, it can also be written. So let's use that relationship over here for the second part. So that gives us Hs by H is equal to rho S by rho L, and we don't want to change this quantity, so let's look at Hs only. So that is rho S by rho L into H over here. So this quantity Hs now can be written as, we have already taken care of this part. This was nothing but rho S naught by rho L naught into 1 plus gamma minus 3 alpha delta theta, and this quantity also will change due to the thermal expansion, and that would be H naught into 1 plus alpha delta theta. This is only the linear expansion, and when I will be combining this term and this term, what we will be getting, rho S naught into H naught upon rho L naught, and combining these two terms, we will be getting 1 plus gamma minus 2 alpha into delta theta. And for this quantity to not change, okay, this term got to be equal to 0, means gamma, that was L and that was S. So gamma L will be equal to 2 alpha S. This is also alpha S. So this is the answer for the second part. Okay, so this was a little bit about the thermal expansion. Okay, and that's it for today. And thank you very much for joining.